Okay, on to same lesson, lesson 6, questions 16, 17, 18, and 19 are the ones we're going to be looking at right now. So, the first question is asking you what's going to be the current at D. So just looking at this, and we'll take just a quick second to throw up some lines so you can see it a little bit better. Current's going to come through here, it's going to split and go this way, split and go this way, split and go that way, then it has to go through D. Whatever's going through that resistor has to go through D. So, we know the voltage applied is 120 volts. So we know our E and we know our R. So we can just simply take 120 divided by 30 for 40 amps. We know 4 amps is going to be going through D. 4 amps. And the next one, they're going to ask C. So what's going to be part of C? We know that all of this has to go through. And coming from this side, we know that this current has to come through, has nowhere else to go, and also has to go through there. It's also being exposed, or being applied to 120 volts. Excuse me, I'm having all the time talking about it. So, 120 divided by 60, we know we got 2 amps flowing down through here. So, at point C, we have to be seeing how many? Don't let it confuse you, don't let it fool you. It's only going to carry the imbalance. So if 4 amps are coming through here, 2 amps are going to go up that way, because that's what's there. And the imbalance between those two is going to be 2 amps. Don't let this stuff confuse you here, because all your neutral is going to be doing is carrying the imbalance. 4 amps is going to flow up through here, 2 is going to go up through that and head back through here, 2 amps. So the next one that's going to be coming in is going to be this guy right here. It's got nowhere else to go, it doesn't have another branch to hop on yet. We know it's 60, so we know that's going to be 2 amps too, coming up there and joining it. We got 40 here. So we know we got 3 amps coming down here. That's what's going to be flowing down through here and heading that way. But, remember, it's only going to carry the imbalance, so right here we've joined up to have 4 amps before we hit this junction. So what's going to happen at that junction? 3 of these amps are going to flow up this way. 1 amp is going to flow through B. Just 1 amp. The imbalance between the 2 phases. I'm going to call them phases. It's what we're used to hearing in the field. It's going to be the most correct term. We should get used to using it. So we got 1 amp flowing through here. Here, we're going to have a little bit more joining in, right? 6 amps is going to be coming up through here. It's got nowhere else to go. It's going to join on it and continue on. So, for the last one, current at A, flowing back on your neutral, 7 amps. So, just to check this real quick, you got 5 amps flowing out of here. Down here you have 6, 7, 8, 10. I'm not looking at this right now. Yeah. So, just what's coming out of both sides. It's got to equal up. So, we have this resistor dropping 6. Just throw it up on there, make it a little bit easier to check it out. There's no other path for current to flow. So we know that we're feeding out 6, 7, 8, 12. Just to kind of keep it straightforward. Just make it so you can look at it and it makes sense. You knew you had 12 amps coming out here, 5 amps there. The imbalance is going to be 7 amps. You hear me double checking myself to make sure I'm getting it right too. So that's how we're solving for current. And on this problem, they're going to throw an extra wrinkle at you. It's going to say this neutral is opened up. So now everything has changed. So we're actually going to end up having to look at this thing a whole different way right now. Because now we're going to be applying different voltages, changing our current, because now there's not a neutral to carry it. So we're going to be changing quite a few things around. Let's take a look at it and see what the relationship is and figure out how we go about it now. So the first part of the question they want to ask is, what's the voltage at R2 out there? I didn't label these, but this is R1, R2, R3, R4, R5. Now, something you can look at it this way. This is gone now. Gone away. Except for that part on the bottom I just erased. That is obviously still there. How about if we do something like this? It's just a combination circuit that we've been working with. And we know that this is applying 240 volts. That's all it's doing now. So now we have to look at it in that relationship. So it's like this right now, but tell me, is there anything electrically different than drawing it like this? Showing these two resistors coming off. Draw another resistor. I know this is small, it's probably hard to see, but it's just me with chicken scratch just throwing out another one. Electrically, same thing. Looks just like it, no difference. So, since we got parallels up here, we could actually even stretch this a little bit farther. We could do this with just a single line. This is all the same point. It can be any way it shapes as long as these three are connected and these three are connected. So, since we can go like this, we would take our reciprocal formula and hit those two out first. 1 divided by 40 plus 1 divided by 60. And 1 divided by our answer there to come out to be simply, let's see, 24 ohms. So let's just take a different color, throw it over here as we're working through it. A little bit bigger, so hopefully you guys can see it a little bit better. This is what we're at right now. So we have this at 24 ohms. So we'll use the reciprocal formula to combine these into one resistor 2 because we're going to make ourselves a simple series circuit. So, if you punch those into your calculator, we're going to come out with our second resistor down here. And we'll just draw right through that way out. You know what else at 10 ohms. So essentially we've broken this whole thing down. And what the first part of the question that they want is they want the voltage across this resistor. This is how we're getting to that point. We know we have 240 volts applied. So we have 240 volts applied. So we know our RT is going to be 34. So we know if we take E divided by R, we'll get our I. So 240 divided by 34 is going to give us our current. Our IT for our circuit is 7.059 amps. So now that we have our current, we can find our voltage drops. I times R equals voltage drop. So we know on this guy out here, we're going to be applying 412 volts. And we take our I times R again down here to get 70.588 volts. Let's add that to what we got up here and see what we're actually getting. 240, almost right on the button. So those are good numbers. We know that's all solid there. So we've solved for our voltage drop down there. And just looking at it, you can see now, if these were all 120 volt loads, you can see on the upper part now you're putting 170 volts to them. They're going to fry. Which is why when you're cutting like a service to a house or a building, you don't ever cut the neutral first, you cut the hots first. Because you could potentially, if it's wired incorrectly inside, you could potentially put the wrong voltages at stuff. 169 will probably fry stuff, but your fridge trying to run it at 70 volts will try to work too much, it'll burn itself up doing that too. It's got to have the right voltage to it to work properly. So that gets us through those ones. And that took care of the next one. So that's a multi-wire, I guess you could say, with an opened neutral. It's essentially just a combination circuit that we've broken down and put to this point. Don't overcomplicate these things, redraw them, just like we did down here and down here. Electrically, these are exactly the same. The power supply still sees it that way. Don't overcomplicate it, don't frustrate yourself on this stuff. So if there's any more questions on this stuff, you guys want to see more stuff like this, you're worried about it, get a hold of me, let me know. I got to know what you need in order to be able to do this stuff for you.